Hey, welcome back. It is day 7. We are on page 32. This is Applications of Quadratics. So we're going to be doing a bunch of word problems now, and we're going to see how we can use what we've learned in the quadratic functions unit so far to sort of figure out these word problems that have some nice little tricky words to them. So number 1, consider a rectangle whose area is 45 square feet. If we know that the length is 1 less than twice the width, then we would like to find the dimensions of the rectangle. So if we represent the width of the rectangle using W, okay, there we go. It's back. We're back. We're in business. Then write an expression for the length of the rectangle L in terms of W. So remember, writing something in terms of means that this L wants to be by itself, so L equals, and then the W is going to be in some sort of expression on the right. So we know that the length is, that's what I've written so far, right? Length, L, is equals 1 less than twice the width. So 1 less than twice the width means that I have to do 2W and then I have to subtract 1, right? 1 less than it. So that's twice the width right there, and then 1 less than it. So there's my expression there. Set up an equation that can be used to solve for the width, W, based on the area. So we know that the area is 45 square feet. So the area of a rectangle is length times width. And in this case, now I just plug in everything I can. So in this case, I have 45 for my area. And instead of length, I'm going to plug in, I'm going to use substitution, right? I'm going to plug this in. So that's 2W minus 1, and then times W. And now we want to solve this equation to find both dimensions, okay? And why is one of the solutions for W not viable? So apparently one of the solutions is not going to be viable. So 45 equals, I'm going to distribute this W. So that would give me 2W squared minus W. And now I'm solving a quadratic. And so what is the first step to solving a quadratic? It has to be equal to 0. Right now it's equal to 45. How do I make that 0? Subtract 45 from both sides. Okay, so now I have 0 equals 2W squared minus W minus 45. Okay, now we can solve this. We have several different methods of solving. I would ask that you go ahead and try and solve this first. Use any method that you want, okay? So, hopefully you paused the video. I'm going to go ahead and factor this because I like factoring. It makes sense to me. So, this is a factor by grouping. I got negative 90. So it has to multiply to negative 90 and add to make negative 1. That's going to be negative 10 and positive 9. But again, you could have used any method. You could use the quadratic formula, plug in A, B, C, however you wanted to do this, okay? Negative 10 and positive 1. Okay, now I'm going to factor over here. And I'm going to factor over here. Did I write 40? Wait, what's going on here? That's a 9. Sorry. Okay. Negative 10 and positive 9 multiplies to negative 90 and adds to make negative 1. Okay. Sorry about that. So I can factor a 9 out. and I get w minus 5. So 2w plus 9 times w minus 5 makes my width either -9/2 or 5. So which of these solutions for w is the correct width, and which one's not viable? Well, w equals 5 is our correct width. This one's not viable. Why not? If you said because it's a fraction, that's not true. Widths can be fractions. That's fine. But if you said it's because it's negative, that's correct. Okay? Can't have a negative width. Can't have negative width. Okay? We're not quite done, sorry. We need both dimensions. I have the width. I need the length. I need to now take this 5, bring it back up to find my length. Keep going there. My length was up here. So length equals 2 times 5 minus 1. And so my length equals 9. Okay? There's my two dimensions. Length is 9, width is 5. And we are in feet. There. Awesome. Number 2. A square has one side increased in length by 2 inches and an adjacent side decreased in length by 2 inches. The resulting rectangle has an area of 60 square inches. What was the area of the original square? Okay. Let's draw some stuff and figure it out. So I'm going to start with the original square. There, I tried to draw a square. It kind of turned out pretty cool. We know a square has the same length and width. So I could label this x and x because they have to be the same. And this is what we are trying to figure out. We are trying to figure out the area of this square. But without knowing the dimensions of the square, we can't figure out the area. However, we take this square and we turn it into a rectangle. And we do that by increasing the length by 2 inches. So I'm going to take this length and I've increased it by 2. So that's x plus 2. And then I've decreased the other side of it. So I've decreased this by 2. So that's x minus 2. And this rectangle we know has an area of 60. So this is now set up to do what we did in the previous problem to figure out the value of x, which we can then use to find the area of the square. So we know that length times width equals area. So length times width equals area. So let's double distribute this. X squared minus 2x plus 2x minus 4 equals 60. Let's combine like terms, set it equal to 0. Subtract the 60 from each side so it's equal to 0. X squared minus 64 equals 0. Now we can solve this. I'm going to go ahead and factor this because it's a difference of perfect squares. Right? X squared is a perfect square. 64 is a perfect square. We're doing a difference. It's minus. So x plus 8, x minus 8 And so we get x equals -8 or x equals 8. Which one are we going to use? It's not going to be -8, it's going to be 8. That's not my answer, but it's what I'm going to use here because now I know that x is 8. So the area of this square is 64. And what are we talking about here? Inches squared. Let me try that again. There. What was the area of the original square? I'm just making sure that I answered the question. So it wanted the area of the original square, so that's my answer, 64 square inches. All right, let's move on to the next page, number 3. We can certainly play around with some word problems that involve strictly numbers. For example, there are 2 rational numbers that have the following property. When the product of 7 less than 3 times the number with 1 more than the number is found, it is equal to 2 less than 10 times the number. Okay, I read that fast on purpose because I thought it was funny. Anyways, when the product means multiplying, right? So I'm going to start by creating like a set of parentheses because I'm going to multiply these 2 things, okay? So when the product of 7 less than 3 times the number, I don't know what the number is, that's going to be x, okay? So 7 less than 3 times the number, what would that look like? What do you think? 7 less than 3 times the number. 3x minus 7. Okay, so that's the product of that with, so this is the other thing we're multiplying by, 1 more than the number. Okay, 1 more than the number. X plus 1. When that product is found, it's equal to 2 less than 10 times the number. So 2 less than 10 times the number is that. We need to find the 2 rational numbers that fit this description. Okay, so there's going to be 2 different values here. So we are going to solve this. Let's double distribute. 3x squared plus 3x minus 7x minus 7. And then combine like terms, set it equal to 0. I'm going to do that all in one step here. We should get 3x minus 7x is negative 4x, and I'm going to subtract a 10x. And then negative 7, and I'm going to add a 2. So we end up with 3x squared minus 14x minus 5 equals 0. Can this factor? Yeah, it looks like there's numbers that multiply to negative 15 and add to make negative 14. So I can factor this into, well, step by step here, 3x squared. Those numbers would be negative 15 and positive 1. And so now I'm going to group this and sort of GCF both sides. Oh, there goes my 5 again. Let me fix the top of that 5. 3x plus 1, x minus 5 is my factored form, which makes my solutions x equals -1/3, and x equals 5. Those are my two rational numbers. We're not talking about rational functions. Right, so if you remember, rational numbers are anything that can be turned into a fraction of integers. So here we have -1/3, which is a fraction, 5, which could be 5/1, right? So yes, those are the answers to number 3. Okay? Number 4. So a lot of times we'll have questions that involve consecutive integers. So we want to just make sure we know what this means. What are consecutive integers? What does the word consecutive mean? It means back to back, right? So integers would be whole numbers. So like if I wanted consecutive integers and I know that one of the numbers is, or the smallest number is 4, then the next consecutive one would be 5, right? Okay. So in general, though, if the smallest number is x, what's the next number? What would that be? How could we represent the next number? So that would be x plus 1, right? Because if I use that same example, 4. So if 4 goes here, and for x, 4 plus 1 is 5. The next consecutive one is 5, so on. Okay? So find all sets of two consecutive integers such that their product, okay, so their product, the product of these two consecutive integers, so x times x plus 1, okay, multiplying them together, that's what product means, is, so equals, 8 less than 10 times the smaller integer. Smaller integer is x. So 8 less than 10x. We should have that. And now we're going to go ahead and solve this. So again, I would ask you to pause, try and solve this by yourself first, and then I'm going to go through it. Distributing it, I get x squared plus x. Setting it equal to 0, moving everything to one side, I get x squared. I'm going to subtract 10x, so that would become minus 9x. I'm going to add 8, and so that would be plus 8. Now I'm going to see if this factors. Multiplies to 8, adds to negative 9. Probably negative 8 and negative 1 would work. And so it looks like x equals 8 and x equals 1. And you're probably saying to yourself, well, wait a minute, those aren't consecutive integers at all, right? They're not consecutive. They're not back to back. But that's true because these are two different answers for the smaller integer, right? These are just x. These are telling me what this is. We now have to say, well, if the smaller integer is 8, what's the next consecutive? Well, 9. So 8 and 9 is one answer. And if x is 1, if the smaller integer is 1, what's the next consecutive? Well, 2. So 1 and 2. That's the next set of integers. All right, and that's how we do those sort of consecutive integer type problems. Number 5. Brendan claims that the number 5 has the property that the product of 3 less than it with 1 more than it is the same as 3 times 1 less than it. Show that Brendan's claim is true, and then algebraically find the other number for which this is true. Okay, so Brendan claims that the number 5 has the property that the product of 3 less than it being 5. So what's 3 less than 5? Well, I'm going to write that out. We're talking about product. So I'm going to multiply this by 1 more than it being 5. So 1 more than 5 is the same as 3 times 1 less than it. So 3 times 1 less than the number. So 3 times 1 less than 5. Okay, so this is his claim. We want to know, is his claim correct? Well, I'm just going to figure this out. What's 5 minus 3? What's 5 plus 1? It's 5 minus 1. Is this a true statement? 2 times 6 is 12. 3 times 4 is 12. Yes, it is. True. Okay, we have shown that his claim is true. Now we have to algebraically find the other number for which this is true. So instead of 5, now I'm just going to replace all these with x's. So x minus 3, x plus 1 equals 3 times x minus 1. And solve. Double distribute, set equals 0, factor, solve. X squared plus x minus 3x minus 3 equals 3x plus 3. Combining like terms, setting equal to 0. Let's see here. X minus 3x would be negative 2x, but then I'm going to subtract a 3x and minus 5x. And then negative 3, but then I'm going to subtract another 3, so that's negative 6 equals 0. This can factor into x minus 6. Had to think about that one for a second. And x plus 1. So x equals hold on, did I do this right? Hold on. X equals 6. And x equals negative 1. Huh. I thought I was going to get 5 as one of my answers. Let me make sure I didn't make any mistakes. X squared plus x. I copied it over correctly, right? Yeah. Squared plus x. Negative 2, negative 5x. Negative 6 times 1 is that. Negative 6 plus 1 is that. Well, that's interesting. Oh, there it is. Got it. There's my mistake. Okay. Let's start over. I'm just going to erase all this. So I didn't distribute the 3 into the negative 1. Uh-oh. Hopefully you guys caught that right away, and you were like screaming at the computer like, what are you doing? Why are you making this mistake? Okay, didn't have to go that far. So double distribute. Again, take 2. X squared plus x minus 3x minus 3 equals 3x minus 3. Much better. Hopefully we'll get x equals 5 as one of my answers this time. So now combining like terms, x squared minus 2x minus 3 equals 3x minus 3. Subtract the 3x. Now I'm going to add 3, and when I do that, it cancels. and I get x squared minus 5x. This is much better because now I can factor this like so. And so I get x equals 0 and x equals 5, which is what I was expecting. So the other number is 0. X equals 0. So this claim, just in case we were wondering, what the product of 3 less than a number with 1 more than it is the same as 3 times 1 less than it, it's 5 and 0. So 0 is the other number. All right. Hopefully that wasn't too confusing. Yes, I make mistakes all the time. It happens. Number 6, a football player attempts to kick a football over a goalpost. It's a good thing to do. The path of the football can be modeled by the function x equals negative 1 over 225x squared plus 2/3 x, where x is the horizontal distance from the kick, and h of x is the height of the football above the ground when both are measured in feet. On the set of axes below, graph the function over the intervals 0 to 150. Okay, well, I'm going to use my calculator for this. I don't know about you guys, but negative 1 over 225 and 2/3, let's just use the calculator. Y equals, I'm going to plug this function in, so negative 1 over 225 is my coefficient on x squared, and I'm going to add 2/3 x. All right, there we go. Now, it does say on an interval from 0 to 150. So even before going to the graph, I can set my window and make my x minimum 0 and my y maximum 150. And let's just hit graph from here. Let's see what happens. Okay, we can see part of this graph. We can't see all of it. What do we need to see more of? We need to see more of the top. We need to see more of the y maximum. So we have to increase the y maximum. So go back to window. And let's increase our y maximum. I don't know, that was 10. How much more does it look like we needed? Who knows? I'll just go up to 50. Does that work? Yeah, that works. Okay. So there's a nice little image of this. What you should not do now is now just try and draw that, because that would not be accurate at all. What we want to do is we want to look at the table and find points that we can plot. So we're going to go to the table and we're going to look for points that we can plot. We're not going to be talking about negatives and negative x values here or negative y values. Not going to go through the ground. I can certainly plot 0, 0. Okay, in fact, that's the first point I'm going to plot. And I'm going to kind of scroll through and try and find other values. So 15, 9, that's a whole number pair that I can plot. I just passed one. 60 and 24. Okay, so 15 I can plot, 60 I can plot, 75 I can plot. Based on those x values, it looks like I might want to go by 15s on my x-axis. So if I do that, let me see. Let's just see how many I would have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I would be done right here if I went by 15s, right? And my whole graph would be in this little small space. So I could certainly skip one here. So let's go ahead and do that. Let's start with this x-axis, and I'm going to skip, and I'm going to get rid of that stupid little thing. And I'm going to make that 15. I'm going to make this 30. And I'm going to create this consistent scale. where I'm going up by 15s every time. So 75, and then 90, 105, 120, 135, and 150. Okay? So now I've got this interval from 0 to 150, because of course this is the origin at 0. All right, so let's go back to the calculator. And I was seeing values of like 24, blah, 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 blah. I can look at all this stuff, right? Or I can just go back to this, go back to the graph. And I kind of want to know, well, what should my y scale be, right? I might not have to, on my graph on the paper, I might have to go up to 50. There's a lot of wasted space here. So what's the maximum? Let's find that out. So let's do second calc, right? And let's do the maximum. And let's go to the left side of the maximum. Hit enter. Go to the right side of the maximum. And hit enter. Enter one more time. And the maximum is at 75.25. So I know that my y value, the maximum, it has to be 25. So could I do like 5, 10, 15, 20, 25? Yeah, I might waste some space, but I might as well just do that. So on the y, let's go 5, 10, 15, 20, 25. Okay. So I've figured out a decent window to put on my paper. Now I start plotting all of those nice points that I found as accurately as possible. So let's go back to 0 on my table and start plotting all the nice points. So 0, 0. Let's plot that right there. And then 15, 9. So 15, 9 would be right about there. That's what happens when I don't use a pen. And then 30, 16. 30, 16. So based on the y values, I probably could have made my y scale a little bit better. I could have maybe gone by 3s or something. I don't know. We'll see if that pattern continues. Probably does, since it's symmetric. 45 and 21. So yeah, if you went by 3s on the y-axis, this would have been a lot easier, a lot more accurate of a graph. But this works too. 60 and 24. And then our vertex of 75, 25. And then I'm just going to go ahead and use symmetry to finish this. I know that all of these values will be equivalent on the other side of the vertex. Making sure I hit the right x value. And there. And there. So now I try to make this look decent. Oh, that was pretty good. I gotta say so. That was pretty good. Determine the vertex of y equals h of x. So what was the vertex? 75, comma 25. That was the turning point right here, right up here at the top. Explain the meaning of this vertex in the context of the problem. So what is the problem talking about? What do these numbers mean? So what is the x? The x is the horizontal distance from the kick. So we can say that when the football is kicked 75 feet horizontally, it reaches a height of 25 feet. The goalpost is 10 feet high and 45 yards away from the kick. Will the ball be high enough to pass over the goalpost? So 10 feet high, 45 yards away. Which one's x, which one's y? Well, x is horizontal, so that's going to be 45. 10 is our vertical, so that's our y. So where would this point be on our graph? 45, 10 would be right here, right? So there's the goalpost. Does this kicker clear the goalpost? Is the football high enough to pass the goalpost? Justify our answer. Well, at 45 feet away, the ball is, if I look at 45, the ball is all the way up here at 21 feet. It's 21 feet high. Height. Hit. High. So, the ball is 21 feet high, which means, yes, it's cleared it by like 11 feet, right? So, yes. It is high enough. Okay? Now, whether it was wide left or wide right, we don't know. But anyways, that's it for unit, what are we in? 5. Unit 5. That's our quadratics unit. Okay? So you guys should be done with your note packet now. And I will see you guys next time.